hopefully.
Yes. We're going to talk about gravitational physics and eccentric binaries.
Good afternoon. Hopefully you will not sleep during my lecture. So I'm going to talk about slightly boring topic. It's called eccentric binaries, and gravitational wave community has some real aversion for that. So let me talk about that and see what's its implications. So I'm from Jena, and so that will be a brief outline of what I'm going to talk about. I will define formally what you actually meant by post-Newtonian accurate gravitational wave phasing. So the words are all important out there, post-Newtonian. Then I will argue that you actually need this procedure called gravitational wave phasing to construct temporally evolving gravitational wave polarization H plus and H cross for comparable mass compact binaries if their dynamics is governed by post-Newtonian approximation. And then I will talk about, of course, in the case of eccentric binaries, and I will explore briefly what are the data analysis implications, both for ground-based and space-based. Things are ongoing there. Okay, so these are the references. I'm going to skip that. Okay, so let me have the customary introduction. So we all know that inspirally compact binaries are the most plausible sources of gravitational radiation for operational, planned, and proposed laser interferometers. There is no guarantee that we are going to see any of these sources. And gravitational wave data analysis groups require H plus and H cross, temporally evolving, and they have to be accurate in their phase evolution. Amplitude can be okay, but the phase of that H plus and H cross has to be very accurate. And then recent advances in numerical relativity imply that post-Newtonian approximation, which is just corrections to Newtonian theory based on general relativity, is a fairly good approximation even when you come very close to the last stable orbit. And in post-Newtonian treatment, compact binaries are just point masses. Okay, so the structure is not important. Two neutrons are also point masses, and this is sort of justified from post-Newtonian arguments and also arguments emanating from observation from timing of binary pulsars and things like that. Good. So what is the post-Newtonian approximation? It gives corrections of the order of v by c raised to 2. So if you put an n equals 1, that's the first Pn. And if you put that n to be something like 3 or 4 or whatever, you get higher order corrections. And these corrections are usually computed based on general relativity, even though you can actually do it for other theories of gravity too. And as far as gravitational wave interferometers are concerned, and if you are interested in the dynamics of compact binaries, in post-Newtonian approximation, we have to tackle two independent problems. They are related. One is to actually computing post-Newtonian accurate equation of motion, which is x double dot. X is the relative separation between these two objects. And then that's not sufficient. You also need to compute post-Newtonian accurate expression for the gravitational wave luminosity. And I will argue why that is actually required. So this is the energy carried away by gravitational radiation if it's moving on a circular orbit. If it's eccentric, you actually have to go and compute other things like energy and angular momentum flux and things like that. And of course the polarization, which is the gravitational wave polarization you are interested in. And since amplitudes are not that important, you can actually use the Newtonian amplitude or the quadruple contribution to that. So schematically this has been achieved here. So the dynamics or equation of motion for two non-spinning point particles in general relativity has been solved up to so-called 3.5 Pn order with respect to the Newtonian contribution. So these are something like 1 over c raised to 7 corrections to Newtonian equation of motion. Okay? Yes?
So for you said the amplitude corrections are...
I'm aware of that. Yeah.
As the phase.
It says LIGO Virgo.
Okay.
Yes, it's important even for advanced LIGO. And that's the reason you'll see that people have been computing those things too. But currently data analysis groups are not interested for the time being. Okay. So the dynamics is known up to 3.5 Pn order, and you will see that it's actually true for the luminosity too. So the luminosity also has been computed up to that relative contribution, even though this actually starts at 1 over C5. That's what I call as 2.5 PN out there. Okay? And then the H plus and H cross, that actually starts at 2 PN formally, but then we call that as a Newtonian. So this is a relative way of calling things. Okay? Whenever it starts at a certain order, you call that as a Newtonian contribution, because from Newtonian arguments you can compute that. Okay? So that's the general way of. So don't confuse it. That's the way the nomenclature exists, and it's a very convenient way of doing things too, right? So if you only know Newtonian dynamics, you can actually compute this contribution to the gravitational wave luminosity or energy radiated from 2-point masses. And I can also compute H plus and H cross, and most of you have done that in general relativity course, right? But you have to be much more careful when you go higher order. Okay. So we have been trying to compute first Newtonian accurate, ready to use. When I say ready to use, it's accurate and very efficient way of constructing such templates for compact binaries along inspiraling eccentric orbit. And so then this is a slightly involved process, even though it can considered to be not that important. The reason is that now we have 3 time scales there. When you consider an eccentric binary inspiraling under radiation reaction, and if they're non-spinning, they're going to be 3 time scales. One is the orbital time scale, and then other one will be that of the precision of the periastron, and then you have the radiation reaction. Okay? And so how do you do that? Well, it turned out that we can actually adapt a formulation which give heavily employed timing formula for binary pulsar, and this is called DD timing formula, or the more derivative timing formula, to do the phasing of eccentric binaries, gravitational wave phasing for eccentric binaries. So let me give the definition of that. It's a mathematical procedure. It gives you temporal evolution of H plus and H cross that reflects the orbital dynamics. Okay? This is crucial because we do not, like in numerical relativity, extract these waveforms. We have to do other assumptions to get the evolution of the orbit. And it turned out that this kind of constructing templates is very close to the way one constructs timing formula. The reason simply is that in the case of timing of binary pulsar, you actually follow the orbit to predict when the phases, when the pulses will come to you. In the case of phase, simply it's the same thing. Okay, so you have to track the orbital phase. That's the crucial thing here. So it turned out that because of that argument, both timing and phasing are equivalent. You can actually do a prescription to compute timing formula to compute gravitational wave polarization for eccentric binaries. And in the timing formula, what you require is a solution of relativistic equation of motion for 2-point objects in an eccentric orbit. Okay, and then with that solution, you can actually predict the observation of pulses from binary pulsar or double pulsar in that case. Okay, and then extract lots of information about the dynamics, geometry, and we know that these are consistent with theory, and you can actually do amazing astrophysics with those things like testing relativity and things like that. So therefore, naturally one expects that the phasing formulation, which should give H plus and H cross, should also reflect what we know about the post-Newtonian accurate orbital dynamics. Okay, and that's what we are trying to do. So I'll go into a slightly technicality here. So this is the so-called restricted post-Newtonian waveform. It's just the Newtonian amplitude computed from the quadrupole moments of the binary. So that's H plus and H cross for you. So it actually depends on the orbital separation R, then its time derivative R dot, the orbital phase phi and its derivative phi dot, and this is the total mass, and eta is this, what we call symmetric mass ratio. Eta is 0 for every 1 over 4 for equal mass. Okay? And R is distance to the binary. You can see that that starts at C4, and that's what I call that as a 2pn term. Okay, but it's a Newtonian contribution. and I is the orbital inclination. So if you have a specific geometry, you can actually kill this signal altogether. I equals pi by 2, there's no H plus, H cross. So all you have to do is to actually solve the dynamics of the binary so that you get an expression, equation for RT, phi of t, R dot t, and phi of t. That's all. Then you get the phasing. Okay. And if you are considering eccentricity in general relativity is a subtle point. It's actually going to be gauge dependent. So this prescription technically will be gauge dependent, even though H plus and H cross you can actually measure. That's consistent because the timing formula is also gauge dependent, but you can still do physics with timing formula. So there's nothing wrong with that. So in order to do that, the orbital phase or orbital evolution, what we did was employed a slightly improved method of variation of arbitrary constant, which are quite common in. Okay. That's the power? I think it's not connected to the. Sorry about that. Yeah, I think that's the red one, right? Yeah. So is the power cord here? Otherwise, I have to put up mine.
Okay, do you have one?
I have, but this will not be compatible with Dell. I have a laptop.
Okay. But it should be around here, I don't understand. Okay, fine.
I don't see any power cord. Yeah, it's.
Fucker. No?
Yeah, I think you have to wait for it.
I is sleeping. Wait. Okay, it's going into sleep modus.
Yeah, okay, it's good.
Okay. Yeah. Nice.
Okay, that's fine. No big deal. Okay, so the game is to obtain what we call as the phasing relation, which gives you the orbital variables as a function of time. And you just plug those things into the waveform and you get the temporarily evolving gravitational wave polarization endgame. So it's actually, since we are interested in the dynamics of the compact binary, it's actually very convenient to split the relative acceleration into two parts. One is what we call as the conservative part. So if the binary is evolving under conservative part, it will not in spiral. It will be always in an orbit which may precess and things like that, but it will not in spiral. And then there is this perturbative part as A prime. So for example, A prime starts at 1 over C5. Okay? So the game is to actually construct some sort of a solution to A0, and it's, if you want templates and you want to be done in very fast and accurate manner, the game is to obtain some sort of a semi-analytic solution to that A0. And then once you get that solution to A0, you get solution to the entire binary dynamics by simply making the constants appearing in A0 as a function of time and obtain differential equation to govern them. Okay? And right now we know the conservative dynamics up to 3pn order. So this is the chart I've showed you. So we know the corrections of this conservative part up to 1 over C6 term. 1 over C5 and C7 are reactive, so that's the reason I didn't put those things in. So we know the conservative part up to 3pn order, so it took a while for people to compute that. Then one can actually show that such a conservative dynamics will allow you 4 integrals of motion. So these are the binding energy and the orbital angular momentum. It's possible actually to define a suitable center of mass frame to do that, and so you get these 4 quantities. And then you just look at the vectorial structure of the angular momentum, and then you can argue that the orbital motion exist in a plane, so that's orbital plane. It's not really guaranteed, but you can show that it is indeed the case. And one can actually demonstrate that even if you put radiation reaction in the case of non-spinning particle, the orbital motion will be in a plane for comparable mass cases. This has been done by Thibaut Damour many years ago. So then we have a clean system. So the binary is moving in a plane, and the orbit can do anything, okay? But there's an orbital plane. So we have something to play with. And then now we look at the solution to the unperturbed equation of motion, which we call as the conservative part of that. And so you can see that, so this is just a functional form of that. One has to actually obtain explicit form for all that by solving the conservative dynamics. So you will see that this is the radial part. So the radial part will have turning points and things like that. And then r dot is just the derivative of that. And there is a phase, and this is split into two parts. And that's actually crucial, that split is required. And then the phi dot, something like that. And so if you look at, so this, if you're familiar with Keplerian kind of parameterization, you can immediately identify that L to be nothing other than the mean anomaly of the orbit. And then, so this, if you are familiar with timing of binary pulsar, you will see that this is precisely the improvement Thibaut Damour introduced into his prescription. Blanford and Tikorski just wrote it like that without realizing that there is a W part out there. Okay, so the phase of an eccentric binary is directly proportional to, linearly proportional to the mean, so true anomaly, not to the mean anomaly. So that's just technicality. But somebody was interested, so I thought I would just mention about it. And this is an important thing. It's a radial period. So it's a period associated with turning points of the orbit. Okay, so where r dot goes to 0, and that's not. And there's other thing too. I mean, so and k is the measure of the periastron advance, and you can actually construct another period n times k. So these are called omega and omega 5 in Emory literature. So they're all there in this prescription. And T0 and lambda 0 are some initial constant. We will keep them, C lambda as some initial constant. We will keep them and we will require them too. So what we have done is, again following the literature of timing of binary pulsar, is to actually construct sort of a Keplerian type parametric solution to the conservative post-Newtonian accurate dynamics. Okay, so let me just refresh your memory about this Keplerian parameterization. So if you know the Newtonian dynamics, you don't have to solve them numerically. There is a way of solving it in terms of the Keplerian orbit. So that's the Keplerian orbit I was talking about. So the radial part is given by the semi-major axis and eccentricity, and you have an angular parameter called u, that's called eccentric anomaly. Then the phase is given in terms of the true anomaly. It's linearly proportional to v. In post-Newtonian also, it's linearly proportional to v. And then this is the famous Kepler equation, which connects time to the eccentric anomaly. And one can actually construct this fairly easily from Newtonian dynamics, and turned out that all the orbital elements will be function of orbital energy and angular momentum. And in post-Newtonian accurate dynamics too, if they are not spinning, you can actually do the same procedure, get something like that for the radial part of the orbit. So the radial motion is parameterized that way. It turned out that all these quantities are now post-Newtonian accurate in terms of energy and angular momentum. And then the 3p accurate phase will have some nasty expression like that. And you will see immediately that there is a linear dependence on the true anomaly, as in the Newtonian case, but it has been modified by that k, which measures the advance of periastron. And so you immediately see that there are different eccentricity. So if you want Keplerian type parameterization for post-Newtonian dynamics, you are forced to introduce different eccentricity for different parts of the orbit. And this is fine. It's just, again, eccentricity cannot be defined in a gauge invariant way, so you are free to do that. And then the Kepler equation looks something like that. So it connects u to time, but it has post-Newtonian corrections like 2pn and 3pn terms like that. Okay, and all these orbital elements and functions can be given in terms of energy, angular momentum, m and eta. And it's convenient to actually solve this equation using something called Mikola's method to solve Keplerian equation. It's a very fast and extremely accurate way of solving it.
Can you say what this is? Which one of Mikola's? Mikola has about 5 different ways of solving Kepler's equations.
So this is a way of solving with one iteration. Okay, so the game is to choose a initial value to u, okay, in such a way that with one iteration you get n up to, for all eccentricities, up to the desired accuracy of 10 raised to minus 15 or something like that.
So what is this way?
I can explain to you. There are steps to do that. Okay? So again, the game is to obtain a trigonometric way of writing this and then from that. Okay?
How does it scale with the time scale?
It's independent of that. So it's actually, that's one of the advantages of that. So yeah, it's just recall in these equations are easy to solve, right? I mean, by root by bisection should be able to do this. But then the initial guess is what creates a problem. And that will misbehave for high eccentricities and some crazy values of L. So he took care of that. So we can discuss that. I haven't aware of he has other methods to solve Kepler equation. I know.
About 5 different.
Really? Okay. This is a paper I worked in, so yeah. Okay. So then to get so what I've been talking about, this Keplerian type parameterization is purely valid for that A0, so the conservative part. So what you do when the dynamics is given fully by that is to make sure that these constants which are present in the Keplerian parameterization, which are like energy and angular momentum, now will be function of time. Okay. Not only that, the way I define L, so there are the CL and C lambda, they're also going to be function of time. So instead of having r dot phi dot, I will have these 4 variables as function of time. And so that will do the trick for me. Okay? And you have to find differential equation for that. And that is fairly straightforward. And I will not go to the details of this derivation. The game is that we want the functional form to be the same both with reaction and without radiation reaction. And then this is just coming from the fact that you have a reactive part, so the energy cannot be conserved and things like that. And this comes from the fact that we impose both r dot and phi dot looks the same even with radiation reaction, even though things are moving in spiraling and things like that. This can be derived with some labor. So that's it. So you have now, from those equations, you can get 4 temporally evolving quantities, and then it's actually very useful to split these two things into 2 parts. One is the secular drift, and the other one is fast oscillation. This simply because of the fact that the equational motion and far zone fluxes will always be off by a total time derivative, and the total time derivatives can always give you periodic fluctuations. So you can actually do that, and then you go and demonstrate that CL and C lambda will not be evolving in a secular manner. They will have periodic variations, and therefore the entire reactive and secular part of this orbital evolution will be purely given in terms of C1 and C2. That's it. So you have pretty much everything under control. You can solve this equation, compute them. And the crucial part one can show, and this has been done up to 1 PN order, is that when you compute the secular quantity of C1 and C2 time derivative, they are identical to orbital average expression for energy and angular momentum fluxes computed independently. So this justifies the balance argument we use up to that order. But this also helps you because you only know equational motion up to something like 1 PN reactive order, but you can use the balance argument and get higher order correction to energy and angular momentum fluxes, and that will be good enough. And people have been working on, Blanchet, Iyer and his collaborators, to get energy and angular momentum fluxes up to 3 PN order for eccentric binaries. So now I will just talk about, okay, so that's good enough. So you have all that. Now what are the parameters you can use to, you know, to represent the binary? It turned out that the orbital binding energy and eccentricity associated with the Kepler equation are fairly good to describe p-n accurate circular orbit. That comes from the fact that the timing eccentricity is fairly close to that. Timing eccentricity is the eccentricity appearing in the timing formula. And then one can straightforwardly obtain orbital evolution equation for the scale energy and ET. So now we are in a position, just impose this reactive evolution into the orbital dynamics, and that will give you temporal evolution for r, phi, r dot and phi dot. Plug that into h plus and h cross. Story ends. You get the gravitational wave from a binary which is precessing and in spiraling. And you can actually do this for the spin, and this is ongoing in ELF. So this is the waveform you get. So it's fairly straightforward. This is actually for 1.10 for LIGO. So you can see that this modulation, I think eccentricity is 0.1 or something like that. So you will see that there's a modulation here, and that's because of the periastron advance, and it becomes circularized very fast, and you get the chirp thing too. So, okay, so that's game. But now there are these details which we have been trying to look into. So how do you get these waveforms? So that's very important. So in order to get a waveform like that, we first have to know a binary up to 2pn order. So the binary cannot be, you can't take a binary in an eccentric orbit, which is Newtonian accurate, and put radiation reaction. That will be inconsistent. You have to make sure that the binary also precesses, because those things are happening at 1pn and 2pn order. So you have to put that one in first, okay? And if you do that, those kind of orbit H plus and H cross are usually known as non-adiabatic templates, okay? And but in the literature, this is not the way it's been done. The templates LIGO, Virgo, and all uses are adiabatic in nature, so they don't really care about this secular evolution at 1pn and 2pn. So they start everything at 2.5pn, and this is usually called as adiabatic templates. And all pn accurate search templates, I'm not talking about EOB, that's not a pn accurate stuff, are purely adiabatic. So then it turned out that actually this was a reply of the referee, Stars, I guess, that see, apparently they did some experiments about non-adiabatic template, but apparently it's been forgotten. They didn't bother to pursue it. So I need to again go back to this diagram to show why it's a problem here. So the dynamics has contributions as 1pn and 2pn before the radiation reaction starts at 2.5p. But if you think that your waveform starts only at that order in the evolution, you're missing this contribution. And this has nothing to do with eccentricity. Okay? So even if eccentricity is extremely small, the thing will precess. And this contribution has to be taken care into fact. I mean, it may be negligible eccentricity-wise, but another thing is that the periastron advance is not linearly proportional to eccentricity. There is a 1 over square root of 1 by e square. Okay. So you put e square 0, there's still an advance of periastron, even though physically it's fairly difficult to imagine what does it mean. Okay. So that's what I keep arguing. So you have to reflect in H plus and H cross what there in the orbital dynamics. You cannot assume that, because the radiation reaction starts at 2.5pn, let this temporal evolution also starts at 2.5p. And so this is actually called non-adiabatic templates. So now we have a manuscript coming in preparation. So actually eccentricity was neglected because of a paper by Martel and Pesson, who what they did was they took a binary in a Newtonian eccentric orbit, perturb it with radiation reaction, and claim that they can put circular binaries to pick this one, which is fine. But we actually have been pursuing that in much more detail, saying that no, before put radiation reaction in, you have to include the secular effects at 1 pn and 2.2 pn before 2.5 pn can bring in. And then it's a problem out there. So LIGO actually searched with 2 pn templates, right? So the 2 pn templates will not be able to pick up even small eccentric binaries of eccentricity 10 raised to minus 4, especially when the number of gravitational recycles is less than, slightly more than 40, something like that. So, because if it's less than 40, anything can match it. Of course, there will be biases and things like that.
What do you mean won't be able to pick it up? Do you mean,
The fitting factor will be something like 0.9 or something.
what do you mean, but it'll still detect it?
0.9, I think they're looking for 0.97 and things like that. Fitting factor.
Okay, but it would still pick it up. It would still see it.
No, I think he's saying that it's not an effectual template now anymore.
Yeah,
It's like, no, you're saying no template in the bank is going to match.
exactly.
No template in the mix is going to make it better than that.
So if you want a fitting factor of 0.97 and use T4 or T1, something completely adiabatic, completely non-adiabatic, there are a list of things people have worked it out, right? None of them can give you a fitting factor of more than 0.9. Okay, so the secular things are picking it up. I mean, and we actually saw this in our other paper, where equal mass cases you have problems that okay. So this is my statement. So we are exploring this now. This adiabatic circular templates, which are post-Newtonian accurate, which has been used to search for gravitational waves, can they actually capture any non-adiabatic templates? And then the question is it adiabatic circular template physically justifiable? And I feel no. So I will give the arguments for all that. So what has been done in the literature, and I have to give references to all that. So this post-Newtonian scheme has been pushed ahead by people like Blanchet, Damour, and Schaefer for the last 20-25 years, and they actually come up with this important for quantities, especially 3pn accurate dynamical orbital energy. So that's given in terms of an omega parameter. I will come back to that in a minute. Then you have 3.5pn accurate gravitational wave energy luminosity, and then you have the amplitude corrections to that, H plus and H cross, and this has been known very recently up to 3pn order. So if you have that, for example, LSC employs T1 template. It's there in T1. I mean, you can actually pick up from the library, LSC algorithm library. So something called T1. It's fairly easy to see what that T1 is. So this is why it's, so you define d phi by dt to be omega, and that omega is the same as x raised to 3 by 2 by m. Okay? And then dx by dt, which is simply given by the balance argument. So it's just rewriting it. And the important thing is that, so if you want to have, say, 3.5pn accurate template, you keep this guy up to 3.5pn and you keep energy up to 3p. So you get a waveform like that. It's very easy to generate and anyone can do this. Or you can compute something called Taylor T4, and this has some history in the current literature. It turned out that numerical relativity, equal mass binaries match this beautifully. So that's called, again, it's the same, just post-Newtonian expand that quantity. And again, you will see that this starts at 1 over C phi. So orbital phase evolution starts everything at 1 over C phi. So we said this slightly problematic here, so we suggested something different. We said that don't do that. Instead of saying that d phi by dt is just omega, give its post-Newtonian expansion. It's just a reparameterization. Nothing else has been done here. So it's d phi by dt given in that form. So you can see that then d phi by dt will have secular evolution at 1pn and 2pn, and of course the 3pn and things like that. And then the reactive parts starts at 1 over C phi. So it just imposes it. And this is precisely what I said. This is a circular limit of eccentric phasing. In the case, if your binary is eccentric, in order to construct the template, you have to perturb a 2pn binary, which is not processing slowly and things like that with radiation reaction. You can't just say that this is omega, okay? So I have the following explanation for that. If you are looking interest only using adiabatic template, they can be considered like the following configuration. So we use balance argument. So the binary evolves along a sequence of circular orbits. Those circular orbits are exact for all the LAL templates because d phi by dt is omega is a definition, whereas those configurations are post-Newtonian accurate in what we suggested. Okay, so we take care of the fact that advance of periastron will not go to zero when eccentricity goes to zero, even though you can't imagine it properly. Okay? So mathematically one can show that it's there in Shapiro-Tikorsky textbooks, any textbook on relativity. For the test particle is good enough. Okay, post-Newtonian just gives corrections. So that's it. So that's what we do. I mean, so we take the binary in a post-Newtonian orbit, which is supposed to be a circular limit of an eccentric configuration, which is the correct astrophysical way of thinking about, and the radiation reaction will slowly kick in at 2.5 p.n. But now the question is that the adiabatic templates match with numerical relativity. So they should be correct, right? Numerical relativity is the actual exact sign. So what about ET? And we actually pursued that just to see what's happening. So this is a comparison of something like, we have something like 10 orbits or something like that. So we actually measure, compare post-Newtonian phase evolution with phase evolution coming from numerical relativity. So this is the accumulated phase difference. And we actually look for them as a, as you change post-Newtonian order from 2 to 3.5 p.m. This is the T4 one I just mentioned about. It matches beautifully with numerical relativity. It turned out to be an accident in the sense that if you include spin or unequal masses, this match will just disappear. But you will also see something like the accumulated phase difference fluctuates. So this is 2, 2.5 pn is 3 is here, 3.5 is there. For another set of template, it starts from here, it goes somewhere here, and then it goes there and it goes there. And this is blame because of the non-uniform convergence of post-Newtonian series. But in our way of doing, which is fairly okay, we see that this is a uniform convergence. But we have some phase difference here, much bigger than T4. It's a fact. I mean, so there is no guarantee that the post-Newtonian has to be so good with, near the last stable orbit. It's there. So which means that for different prescription, numerical relativity meets Pn as different points, but it still is fairly good. I mean, you're talking about 1 radian when you have something like 20 gravitational wave cycles plus. And so we said, what are the issues about? So let's assume that what are the data analysis consequences of this, and that's fairly easy to do. What we did in collaboration with Sukanta Bose and my student Manuel Tesmer in EN is that we assume that the gravitational waves are given by ET, that the template we talked about, because it's not there in LAL. So assume that that's the circular limit of eccentric phasing, and we try to capture it with T1 and T4 and F2. These are the usual post-Newtonian templates used in the literature, because there have been papers written with that, and it's there in LAL. What we found was for equal mass binaries, adiabatic templates are neither effectual or faithful, in the sense that effectual means the fitting factors will be below 0.97. Fitting factor is something like drop in signal to noise ratio. You want no drop in signal to noise ratio. It's more than 0.97, okay? Less than 0.97. Then you can simply lose the event. And when I mean faithful is that, so there will be a gravitational wave signal coming. There is no guarantee that your template will pick up with exactly the same parameters. So the masses can be different. So if they are very close, you will see that your template is very faithful. So what we found is that adiabatic templates are neither effectual or faithful compared to these non-adiabatic templates. Yes?
But you've taken the Taylor ET as being the true signal.
Yeah, because...
But if you go back to the previous slide,
yeah,
then the Taylor ET is worse than the T1 and T4.
Right.
In virtually all cases, and Taylor T1 and T4 are closer to the numerical.
Yeah.
So wouldn't it be better to take the Taylor T4 as your true signal and see how well your ET does against the Taylor T4?
I mean, that's, but we are, but that's fine, right? Because we are doing fitting factor.
Yes, but
so
if you take
it will not change anything.
If you take a template which is, say, you have a template which is inherently wrong.
This is not inherently wrong in the sense that...
saying hypothetically,
yeah,
if you have a template
sure.
which is inherently wrong, and you then assume that this inherently wrong template is the true signal, and then you try and match all other families of templates against that. If they don't match this inherently wrong template, you can't then kind of make the kind of insinuation that all these other templates must be wrong because they didn't match the inherently wrong.
No, we are not saying that. We are saying that adiabatic templates are incompatible with non-adiabatic templates. Okay? And non-adiabatic templates have its origin from the zero eccentricity limit.
Yes, but from this plot here, it shows that the adiabatic templates are actually more effectual.
Only during the last, only during the last few cycles. Okay? So the cases we consider, there were 1.4, 1.4, 10, 10, where numerical relativity simply will not be able to give you such a phase match, right? So if the total mass is something like 30, yes, numerical relativity can be used to get templates. There's no problem. But if the total mass is something like 1.4, 2.8 or 10 or 20, so, and we actually did this, we had the same thing for the fitting factor where we said we will not stop at 6, we will stop at 10. We still have the problem. But we know that if you match Pn with NR around 10m, right, you will see that there's hardly any difference in any of these templates. It will be small differences, but you can't explain that for what we have seen. You know what I'm saying? So you don't stop at 6, I mean, so this is, it's not even at 6, I mean, it's somewhere closer. So then you see this, okay? So I can do the fitting factor computation where I stop not at 6m but it's at 10m, but still I have the same statements to make. And there's a reason for that, right? Between 6 and 10, there's not many cycles. All the cycles are behind. And there is the dephasing. So, and then unequal mass binaries, that's very good because now unequal mass binaries, I have a freedom because my eta parameter can, it's a fixed up to 0.25, right? But unequal mass cases, that's below. So I can push that one all the way up to 0.25. I have a freedom. So I get high fitting factor. So they're effectual, but they're very unfaithful. They're so unfaithful in the sense that if you try to find gravitational wave detection with a couple of interferometers, they will miss that ellipse they're talking about. Okay, so coincidence ellipse is a problem there. So we actually mentioned that in the paper. So again, I will not claim that ET is superior or anything. It has some basic philosophy in the sense that I try to reflect the orbital dynamics into the phase evolution, and that's the actual definition of gravitational wave phasing. And then we try to explain it, and this is what happens. Okay, so and in order to answer your question, we are doing something, and the paper will be out soon. So we took both a new version of EOB and T4. Both are matching with numerical relativity up to unprecedented accuracy for when there are something like 30 orbitals, 30 gravitational wave cycles. So which means for initial LIGO that's around 30, total mass is 30. So we did the same fitting factor with EOB as the signal and T4 as the template. This new EOB is not there in GLAD, so that's the reason we can see. And the fitting factors are again going in that direction, exactly like what, because EOB can be considered as a gauge-dependent non-adiabatic template, and it actually incorporates these conservative parts because it's Hamiltonian based. So that's the point. So we are interested in LISA data analysis. What are the implications for LISA? And that's what I'm here and trying to talk to Ed and others, so staff. So I think I will stop.